Every single day, millions of us drive over bridges without giving them a second thought. They just work. But what if I told you that inside the simple, clean lines of a typical highway overpass, there's this extraordinary story of engineering genius, a constant, invisible battle against physics, all designed to last for a century? Well, today, we're going to uncover that story.
Okay, so let's start with a site that is probably super familiar to all of us. This is a side-on look, what an engineer would call an elevation view, of a pretty standard concrete bridge. It looks clean, simple, almost boring, right? It's just a quiet, reliable part of our world that seems to cross that gap with zero effort.
Yeah, but that effortless look, it's a total illusion. The real question, the one we're going to dig into, is what's actually going on inside. What does it really take, in terms of math and physics and just pure brain power, to make sure this thing can handle traffic, weather, and time itself for 100 years or more?
The answer is in here. This is the blueprint. And it's not some simple drawing, it's a 600-page design manual from the Federal Highway Administration. And you can think of it as the secret instruction set for building this modern marvel. So today, we're going to use it to peek inside the mind of a bridge engineer.
First things first, let's break this thing down. We're going to do a little dissection, you could say, and take a look at the basic anatomy of our bridge. So engineers, they always start with the big picture. Our bridge here is made of two main spans, and each one stretches a pretty incredible 110 feet. And right there, that's the fundamental challenge. How in the world do you get a beam to cross that huge distance without it just sagging and breaking under its own incredible weight? Okay, so now let's slice this thing open. Imagine taking a giant saw and just cutting a piece out of the bridge. What you'd see is this: the flat concrete deck up top, that's the road we drive on, and it's all sitting on 6 absolutely massive concrete beams. Engineers call them girders. And these girders, these are the real heroes of the whole story. They're the backbone. Each one is 72 inches deep. That's 6 feet tall. These giant eye-shaped behemoths are doing all the heavy lifting, carrying the weight of the road, the cars, the trucks, everything. But how on earth do they do it? Well, this brings us to the absolute core concept, the engineering magic trick that makes these incredible spans possible. It's a kind of superpower that's built right into the concrete itself, and it's called prestressing. So what is it? Well, think about regular concrete. It's fantastic when you squeeze it, it has great compressive strength, but it's actually really weak when you try to stretch it. Prestressing is the genius solution to that problem. It's the idea of squeezing the concrete, putting it under a ton of compression before it ever has to support a single car. This pre-squeezing basically gives it a kind of super strength, letting it fight off the stretching forces that would normally just crack it wide open. It's brilliant. Now, it might sound complicated, but the idea behind it is actually super simple. Think about it like this. Picture a row of books. If you try to pick them up just by grabbing the ends, they're all going to fall, right? Of course. But what if you squeeze them together really, really hard from the sides? Suddenly, you can lift the entire row as if it's one solid beam. That compression you're adding creates this internal force that holds the whole thing together. That is the exact same principle at work inside our bridge, except instead of hands, engineers use these incredibly strong steel strands. They call them tendons. They thread these tendons through the girdle mold and then stretch them with massive hydraulic jacks before they pour the concrete. Once the concrete hardens around them, they release the tension. The steel strands try to snap back to their original length, and in doing so, they transfer all that force into the concrete, squeezing it from the inside out. That constant internal squeeze is the girder's secret weapon. Okay, so having this superpower is one thing. Knowing exactly how to use it, that's a whole different ballgame. You see, the entire design process is really just a constant battle against a whole host of invisible forces that are trying to tear the bridge apart 24/7. First, you've got the obvious enemies. There's the dead load, which is just the bridge's own colossal weight, every last bit of concrete and steel. And then there's the live load. That's every car, every single 18-wheeler, and even the powerful, shuddering force of a truck slamming on its brakes. You have to account for all of it. But then you have the slow enemies, the more sneaky ones. There's something called creep. That's the tendency for concrete to slowly deform over decades, almost like a glacier. There's also shrinkage, which is the tiny amount the concrete actually contracts as it dries and cures. And then there's fatigue. Think of it like bending a paperclip back and forth. Each car is just one tiny stress, but after millions and millions of cars, that stress adds up and can cause weakness. The design has to predict and fight all of this for the next 100 years. So, how do you fight all these forces, both the obvious and the sneaky ones? Well, you fight them with math, an incredible amount of math. And this next part is all about how those abstract numbers get turned into the physical reality of the bridge. Just look at this. This isn't just some flowchart. You should think of it as a roadmap for survival. This is for just one part of the process, called flexural design, which is basically making sure the girder won't bend and break. It is a crazy, meticulous, step-by-step decision tree to account for every possible thing that could happen. Every single box, every question, has to be answered perfectly. And inside those steps, you find equations that look like this. Now, we don't need to know what any of these variables mean. What we do need to appreciate is the incredible precision of it all. This particular formula helps predict how much of that pre-stressing force will be lost over time because of that concrete creep we just talked about. It's literally a way of looking decades into the future to see how the bridge is going to behave. And here's where it all comes together. This is the payoff. After all those pages of flowcharts, all those complex formulas, after calculating for every single one of those forces, it all boils down to a number. A single, specific, non-negotiable number. This one right here, 14.65 square inches. That is the exact amount of steel reinforcement needed in the deck right over the central support. Not 14, not 15. It has to be that precise, because that single number's purpose is to help keep the whole bridge standing. So after peeling back all of these layers, from the basic parts to the physics to the math, we can kind of zoom back out, and hopefully we can see that familiar, simple structure in a completely new way. And I have to share one last thing I found buried deep in this manual because I just love it. It turns out engineers aren't just designing for physical safety, they're designing for our peace of mind. This quote admits that a huge concern is our unfavorable psychological reaction if a bridge bounces or deflects too much. The bridge might be perfectly safe, but if it doesn't feel safe to us, they know they still have a problem. It's just this wonderfully human detail in a book full of cold, hard math. So the next time you drive over a bridge, maybe you'll see it a little differently. Not just as a slab of concrete, but as this carefully balanced, pre-stressed marvel that's constantly fighting invisible forces. And it kind of leaves you with a question, right? What other hidden genius, what other secret instruction sets do we drive right past every single day?